Ladies and gentlemen, we are back with another episode of our hit Solve It series, where you will get complete past paper solutions with explanations that a mere mark scheme or examiner report will not give you. It'll be a quick revision of the entire syllabus, and with a look at the latest paper formats, it will equip you with all that you need to ace your next exam. So, without further ado, let's get started.
Assalamu alaikum everyone. This is Fahd Ansari and I'm here to help you conquer chemistry. So far in the SolveIt series, I've only looked at the Cambridge International AS level chemistry, paper 1, which is the multiple choice paper. Now in this episode, we'll be looking at the A level chemistry, paper 5. And this one is the May June 2022, paper 5, variant 2. This is the planning, analysis, and evaluation paper, which is basically about experiments and all there is to do with the lab. All right. And with this paper, we're going to cover everything there is to paper 5, including how to draw diagrams, what variables to take care of, safety precautions, weaknesses and improvements to experimental procedure, how to draw graphs, and how to calculate gradient and do other calculations associated with experiments. So without further ado, let's get started on this particular paper. Now over here we have a long drawn out procedure, and I want you to pause the video over here, read through the entire procedure, and then we're going to get to part A. All right. Hopefully you paused that video, so let's get to part A. Now it says you need to complete figure 1.1 over here to show how the apparatus should be assembled for the collection and measurement of gas, right? So if you look back at the equipment available in this list, you will see that you have everything except gas syringes. So we'll not use this for the collection of a gas. What we do have though is a water trough and a 250 cubic centimeter measuring cylinder for the collection of gas. So the method that we'll be using is collection over water. Hydrogen gas that is being made is insoluble in water, so this is a suitable method. So let's draw the apparatus that is necessary for this. First of all, we draw a nice little water trough, and we're going to draw an inverted measuring cylinder. So the mouth is near the bottom, and this is going to be immersed in a level of water that is already present. By the way, the measuring cylinder will be full of water up to the top over here, and so the pressure of the gas that is produced in this sidearm conical flask is going to push the level of the water down, and so it's going to make space for the gas at the top. All right, so to transport the gas, what we're going to do is we're going to have a delivery tube. It's going to be nice and flexible, and just complete this over here. All right, and so that gives us the diagram. So now we need to label the diagram. So this is going to be a water trough, and this is going to be your inverted measuring cylinder. And we're going to have a delivery tube right here. Now we need to make sure that the gas does not escape, right? So one easy method to do this is to make sure that the delivery tube is attached tightly at the sidearm. All right, So some of the delivery tube should cover the side arm conical flask, and so that will ensure that no gas escapes through this particular connection. All right, so let's move on. Now it says over here that the surface of the magnesium ribbon has an oxide layer, and we need to prepare the piece of magnesium ribbon before it is used in this experiment. So we need to remove the oxide layer so that the magnesium beneath reacts with the HCl to produce hydrogen gas. So what we're going to do is we're going to scrape off the oxide layer, and we can do this using sandpaper. All right. Sandpaper allows for scraping and smoothing of surfaces by friction, and that's what we're going to do here. Now part 2 says state what additional information about the magnesium is required before the experiment is performed, right? So now here's the thing. We will be measuring the volume of hydrogen, and in order to define the molar volume of hydrogen, we need to be able to divide the volume of the hydrogen by the moles. And the moles of hydrogen will be obtained from the moles of the reactants, which are magnesium and HCl, right? So for HCl, we know the volume and we know the concentration, so we can find the moles of HCl, but we don't know yet if it's an excess or if it's limiting. So just to be absolutely sure, what we're going to do is we have the magnesium, which is a solid, so we should find the mass of magnesium before we proceed. So I'm going to write mass of magnesium is important. That's what we need to gather. All right, now a molar calculation. It says show by calculation that a volume of 30 cubic centimeters of 0.5 mole per cubic decimeter HCl is enough to react with 0.16 grams of magnesium ribbon. All right, so now we're going to do this by finding the moles of HCl first. So this will be the concentration, 0.5 times the volume. The volume is 30 cubic centimeters. This is going to be divided by 1,000 because we need to convert cubic centimeters into cubic decimeters. Right, so this turns out to be 0.015 moles. Then what we'll do is we'll find the moles of magnesium. This will be 0.16, the mass, which is given over here. We will divide this by the AR of magnesium. You can look this up from the periodic table. And so this will turn out to be 6.58 into 10 to the power of minus 3 moles. All right. Now what we are going to do is look at the molar ratio between Mg and HCl. Now, according to the equation, 1 mole of Mg reacts with 2 moles of HCl. Now, I'm going to use the moles of HCl over here, 0.15. And according to this ratio, I will try to find the moles of magnesium that are required to react with this much HCl. So I will do a cross multiplication, and so X turns out to be 7.5 into 10 to the power of minus 3 moles. That's the amount of magnesium that would react completely with the HCl. But in reality, we have only this many moles of magnesium. So we have less magnesium than what we need to get rid of all the HCl, right? You require more magnesium to get rid of all the HCl than what you have, and so that means that magnesium is the limiting reactant and HCl is in excess. And so that tells us that we have more than enough HCl to react with the magnesium, which is the limiting reactant, okay? Now part 2 says, state why it is not necessary to use a burette to measure the 30 cubic centimeters of HCl. Well, the reason is that it is in excess, right? So we're already going above the amount of HCl that we actually require. So it doesn't need to be measured that accurately. So that's what I'm going to write. So HCl is in excess. All right. So that is enough for an explanation. HCl is in excess, right? It's not the exact amount that you need to react with all of the magnesium. So it doesn't need to be measured that accurately. Right. Now it says the student waits for 2 minutes before taking a reading of the volume. So just why the student waits for 2 minutes. This is happening in step 7. So let's go back up. It says step 7, wait for an additional 2 minutes. This is until the final volume of gas collected is constant, right? So we've already waited enough time to make sure that the volume of gas is constant, no more is being produced, and then we still wait for 2 more minutes. Why? Now, the reason for this is, if you look up at the question, it says that we want to find the molar volume of hydrogen gas at room conditions, right? Now, obviously, in this reaction, some heat will have been exchanged with the environment, so the temperature of hydrogen gas may be a little different from room conditions. That's why you wait after the reaction is over for the gas to return to room conditions so that you have an accurate volume under those conditions that you want. So the answer to this part is that to ensure hydrogen gas returns to room conditions. All right. Okay, next. So we have 146 cubic centimeters of hydrogen gas that is collected, and we need to calculate the percentage error. Okay. Now, if we go back up again, says over here that for the collection of the gas, we have a 250 cubic centimeter measuring cylinder with 2 cubic centimeter graduations, right? So that means you might have a marking that starts with 0, then you have the next marking which is 2, and then 4 cubic centimeters, and so on. So what if the liquid level, the level of the water, is somewhere between these two, right? So you would guess that it is 1 cubic centimeters, right? So the error in each reading is half of the least count. The least count is the smallest volume you can accurately measure, which is 2. And when you divide that by 2, you get 1. And 1 is the error in each volume reading. And so we're going to use this error, all right? And we're going to divide it by 146 and then multiply this by 100, and this turns out to be about 0.68%. And so we're going to write this over here. All right. Now it says calculate the molar volume of hydrogen gas using the student's results from this experiment. So we need to calculate it in cubic centimeters, right? So we're going to use 146. We don't need to convert it into cubic decimeters, right? And we need to divide it by some moles. It's going to be the moles of hydrogen. Now, if I go back up here, we know that magnesium is the limiting reactant. So we're going to use its moles over here to find out the moles of the hydrogen. So if I look back at the equation, the ratio between magnesium and hydrogen over here is 1:1. And so what I will do here is I will use the moles of magnesium, which is the same as the moles of hydrogen gas. All right. So we use the volume divided by the moles, and that gives us Vm, the molar volume. And this turns out to be about 22,174. All right, this is rounding it up to the nearest cubic centimeter. Okay? Right. Now, it says over here that the student's experimental value for the molar volume of hydrogen is lower than the value coded in the table of reported values, right? And that value is 24,000, all right? And we have a lower volume. So what that means is that the volume of hydrogen gas that was collected was less than what we would have liked. How is that possible? The experimental weakness could be that hydrogen gas somehow escaped. Let's look at the procedure and see if it is possible that this might have happened. All right. So it says over here, if you take a look at step 4 over here, it says place the magnesium ribbon in the conical flask. All right. We already have in step 2 poured the HCl into the conical flask. It's already there. Then in step 4 we place the magnesium ribbon in the conical flask again, and then in step 5 we are going to stopper the flask. So there might be a delay in stoppering the flask. That is the stopper over here. If we have that delay in stoppering the flask, then some of the hydrogen might escape, and this is a very quick and vigorous reaction, and so that is highly possible that it might have happened. Okay, so that's what we're going to write over here. Experimental weakness is that some hydrogen might have escaped or might escape between adding magnesium and stoppering the flask. And we saw that this was basically between steps 4 and 5. So an improvement could be that we could keep the magnesium and HCl separate from each other, stopper the flask, and then mix them together. One way we could do this is we could tie the magnesium ribbon to a string, and we could keep that suspended above the HCl, stopper the flask, and then lower it into the HCl. So I could just say that keep the reactants separate, stopper the flask, and then allow them to react. All right, so this would be the method or improvement that we could go for over here. So this was the question number 1. Question number 2 is going to be all about the graph and data analysis and everything. So let's get right into that. All right, let's take a look at question 2. Again, I'd like you to pause the video, read through the entire procedure, and then we're going to get started with part A. All right, let's take a look at part A. And it says over here, state the independent variable. All right. Now, if you take a look at this statement over here, it says a student plans to carry out an investigation to find how temperature affects the initial rate of decomposition. All right. So now you need to look at what affects what. Okay. Over here, you can see that the temperature, if you change the temperature, it affects the initial rate. All right. So by varying the temperature, you will vary the initial rate that is dependent on the temperature, right? So the temperature is what you will change yourself. That is what you will vary. So that is your independent variable. That is the temperature. All right. And by the way, dependent variable is what you measure as a result of the independent variable being changed by yourself. All right. And yeah, that's basically going to be the initial rate. All right. Anyway, now we need to state two variables that need to be controlled. In other words, they need to be kept constant. All right. So what two things need to be kept constant? Well, you want to make sure that nothing else affects the rate of reaction except for temperature. So that means concentrations of the reactant and the catalyst will remain constant, right? That's another factor that could affect the rate of reaction, the concentration. So we'll keep that constant, okay? So we can keep the concentration of the reacted H2O2 constant, and we can keep the concentration of the catalyst Ki constant as well. Another thing that you can keep constant is the amount of the reactant and catalyst. So apart from the concentration, we could also say we can keep the volume constant. All right. But that will become 4 variables, so it's not necessary to write all of these down. All right. Now, one very important question that shows up a lot in paper 5 is about preparing solutions, right? So it says over here that we need to prepare 250 cubic centimeters of 0.1 mole per cubic decimeter H2O2 from 0.5 mole per cubic decimeter H2O2. Okay, so now for this, there's a very simple formula that we can use, all right? And that basically keeps in mind that whether you have a concentrated or dilute solution, the moles of the hydrogen peroxide in both are going to be the same, all right? And we can find the moles using concentration multiplied by volume. So we will use the formula C1V1 equals C2V2, right? Ensuring that moles of H2O2 do not change, right? So C1V1 basically involves the more concentrated solution, right? We have 0.5, which is the greater concentration. The volume is what we want to find. And in the dilute solution, 0.1 is the concentration and V2 is the volume, which is 250, right? That's the volume of solution we want to prepare. Now we can rearrange this, and V1 turns out to be 50 cubic centimeters. All right. Now we need to make sure that we use the most accurate pieces of equipment possible for making a solution. So we will use a burette to measure this out. All right. So we need to write numbered steps. So step number 1 is add 50.0 cubic centimeters of H2O2 from a burette to a. Now, whenever we want to make a solution, we will always use a volumetric flask in order to do the dilution, right? And because we need 250.0 cubic centimeters, that's going to be the capacity of our volumetric flask. To a 250.0 cubic centimeter volumetric flask, that's what we'll do first. All right, we have used the burette and we have transferred it to the volumetric flask. Now the next thing that we're going to do is we're going to dilute it. And we use distilled water for it, not just tap water, distilled water. You need to use that word, otherwise you lose the mark, okay? So you make up the solution to the mark, the capacity mark of the volumetric flask, which is at 250. Make up the solution to that mark using distilled water. All right. So we have these 2 steps, and 1 mark is for calculating exactly how much of the concentrated hydrogen peroxide we need. All right. Now, this next part says that hydrogen peroxide causes eye and skin irritation. So we need to give a safety precaution other than wearing goggles, right? Goggles will protect your eyes. What will protect your skin? All right. Now the skin of your hands is actually what is going to be most likely to be exposed to the H2O2. So what you can use is chemically resistant gloves. All right. All right, let's take a look at the graph question. So we have been given a table and we have to fill it out. So we've been given the temperature, which we are varying, that is our independent variable, if you remember. And we have converted this temperature from degrees Celsius to Kelvin. That's an easy process. You just add 273 to the temperature degree Celsius, you get the temperature in Kelvin. Now what they're asking us to do is to take the reciprocal of the temperature in Kelvin. So I have 293 over here, so I will divide 1 by 293 for the reciprocal, and this turns out to be 0.00341, right? Now over here, the instruction says that I have to record the values of 1 over t to 3 significant figures. That's exactly what I've done over here. And then we have the initial rate that's given in mole per second. All right. And now what we need to do is we have to take the initial rate and input it into the log function, right? Okay. So this is the log button on your calculator, right? Log to the base of 10. So that's what I'm going to do. Log to the base of 10 of 5.75 into 10 to the power minus 6. That gives me minus 5.24. All right, again, to 3 significant figures. I have to make sure that I round these off correctly. Now I'm just going to fill in the rest of the table. And with a snap of my fingers, the values are ready. So now here's the thing, I've made sure that all values are to 3 significant figures for both 1 over t and log of initial rate. Now, one little tip that I would like to give you here is be careful with your rounding, okay? Especially this last value over here, minus 4.20, from the calculator, this actually came out to be minus 4.199, something like that, all right? So when you want to round it to 3 significant figures up till this point, what you're going to do is you're not going to write this as minus 4.19. Okay, that would be incorrect. And that would result in 1 mark being lost for this entire column just by making one value incorrect. All right. So what we'll do over here is when we drop the 9, we're going to add a 1 to the previous digit. That makes it 10. And so we will add a 1 to the digit before that as well. So this becomes 4.20, right? Minus 4.20. Don't forget the sign. So that is how you make sure that the rounding is correct. All right. Now we have to draw the graph and circle the anomalous point on the graph as well. After plotting all the points, we have to use a cross and we have to draw a line of best fit. So for this, I'm going to switch over to my other application with the graph ready for us. All right, maybe I lied. The graph is not exactly ready, but the grid is here. All right, so we're going to get to work on this. Anyway, so the first thing we need to look at is the scales that have been decided for us by the examiner. So let's take a look. So if I take a look at the y-axis, I have over here minus 4.7 and minus 4.8. And so in between them, if I count, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 small squares, all right? So I have 10 small squares or 10 boxes, and the difference between these two readings is of 0.1. So if I divide 0.1, the difference between minus 4.7, minus 4.8 by the number of boxes, that's going to give me the difference between two consecutive small squares or boxes. That's going to be 0.01 per box. All right, that is my scale for the y-axis. Okay, now let's take a look at the x-axis. All right, so over here we have these readings 0.00310, 0.00320. So the difference between these two is 0.0001. All right, and if you count carefully, there are 20 boxes between these two markings, these two readings. So when we divide by the number of boxes, this is going to give us 0.00005. That is per box. So it's a very small scale, but it'll help us plot the graph more accurately. All right. So now that we have the scales, let's plot the points. So the first point that we're going to be looking at is 0.00341 and minus 5.24. Okay, so if I look closely over here, this is 0.00340. So if I count two boxes, this is going to be 0.00341. All right. Now, what I'm going to do is I'm going to bust out the ruler. All right. And I'm going to draw a vertical line from this point upwards. All right. Now what I'm going to do next is to locate minus 5.24. All right. So minus 5.24 is over here. So 1, 2, 3, 4. This is going to be minus 5.24. So if I bring out the ruler once again, just make this horizontal and draw a horizontal line from this point onwards. And then I'm going to make sure that these two dashed lines that I've drawn are going to intersect. All right, I've found this point of intersection over here. So I'm going to draw a nice little cross over here. Make sure that it falls neatly on the point of intersection of these dashed lines. All right. Now, granted that you don't need to draw these dashed lines, you could just use the ruler and locate the intersection of these lines in your head and then draw a cross over there. But you have a lot of time in the P5, in the paper 5, so you can easily go ahead and do this. All right. So I've plotted one point over here. Okay, let's plot another. So we have 0.00336. So this one is going to be 0.00335. All right. So two boxes after it is going to be 0.00336. Okay. So again, bust out our ruler. And 90 degrees, draw a vertical line, make sure that it is not too far away from the point where you want to draw this vertical line. Okay, all right. Now the y coordinate, if I remember correctly, was minus 5.10. Right, we can always refer to our table up here. All right. Yep, it's minus 5.10. So let's rotate this. Draw a horizontal line from that point on the y-axis. This is 5.10. Okay. Draw a horizontal line and make sure these two lines intersect. Found the intersection. And so this is going to be a crossover here. All right. So it's going to become tedious watching me plot all these points. So I'm going to be right back after plotting all the points. All right, so now I've plotted all the points and it's time to draw the line of best fit. Now, according to the instructions, it says you have to draw a line of best fit, all right? And here's one tip for you. It will always say a line of best fit, and it is possible that the points might lie on a curve instead of a straight line. So you will draw a curve in that situation and not a straight line. Don't force it, okay? The line over here is a generic term. It could either be straight or curved according to the points that you've plotted, all right? So in this situation, you can clearly see that there's a line going down from left to right. So we're gonna draw that straight, no curves here, all right? So now let's adjust the ruler according to the points, and we're going to draw a straight line through these, or most of these anyway. All right. Bring this as close to as many points as you can. And when you feel comfortable enough, draw. All right, let's take a look. Now we have to make sure that the points are close enough to the line, and if there is any visible space, make sure that an equal number of points is above and below the line. So you can see that we have this point over here that is a little above, and this point over here that's a little below, right? So there's 2 points above and below the line. The rest of them are pretty close enough. And whenever you draw the line of best fit, there will always be one point that does not fall on the line, that is far away from it. And that is going to be your anomalous point. So always read the part after the part question that tells you to draw the graph. It will pretty much always ask about the anomalous point. So you have to keep in mind that there will be one point that does not fit in. All right, so we have circled the anomalous point, and we want to find out the reason why. All right, normally whenever you have to circle the anomalous point, you will be asked for a reason. So over here, the recorded temperature has resulted in a value of 1 over T to be a little lower. All right, so that means that recorded temperature is actually greater, all right, than the expected value or the actual value of temperature that is represented by the line of best fit. But the point that is further away from the line than the others tells us that 1 over T was lower. That means T, the temperature, was higher, the recorded temperature is higher than the actual temperature represented by the point on the line. So that's what we're going to write over here, that the actual temperature was below. All right, now below what? You need to check out that point again. So this is the point at 0.00325 over here. So let's check that out. What temperature did it correspond to? Corresponded to 308 Kelvin. All right. So the actual temperature was below the recorded temperature of 308 Kelvin. That's what we're going to write. Perfect. So let's move on. Now the next thing that we have to find out is the gradient. All right. So let's select points for that. Okay. So whenever we select points for the gradient calculation, we have to make sure that these 2 points have at least half of the straight line of best fit between them. All right. So let's say I select a point that looks something like this. All right. Now remember, we're not going to choose any data points. We're going to choose any point on the straight line itself that crosses through a corner of a box or small square. Okay. So we have this point over here. So let's read this off. All right. So on the y-axis, we have 1, 2, 3, 4 small boxes. So that's going to be minus 4.34. All right. And for the x coordinate, let's take a look at that. So we read this down to the x-axis. Let's keep going down, see where this leads us. Make sure that it is parallel to that vertical line that you want to draw the dashed line on. And over here, this is one box behind 0.0031. So we're going to say that this over here is 0.003095. All right, because we know that this is the value per box. It's 0.00005. All right, so we have selected one pair of coordinates, and we're going to write this down before we forget. So it's going to be 0.003095. That's the x value. The y value is minus 4.34. All right. So that's going to be our first ordered pair. All right. Now, for the second pair of coordinates, let's just choose a point over here. Let's say towards the end of the line, we have one over here. Okay. So let's take a look at this. So the x value should be easy enough to find. This turns out to be two boxes or small squares behind 0.0034. So I'm going to write this as 0.00339. All right. Now read off the y value. All right. I know this tends to be a little tedious. That's how graph questions are. You have to work pretty hard for them. All right. There's no shortcut to success, fellas. Another tip for you. Okay, so dashed line all the way to the y-axis, and this is one small square or box above minus 5.2, so that's going to be minus 5.19. All right, so this is minus 5.19. So let's write this down again before we forget. It's going to be 0.00339 minus 5.19. All right. So we have this pair of coordinates, and we're going to use this to calculate the gradient. The gradient is always delta y divided by delta x, which is basically y1 minus y2 divided by x1 minus x2. So y1 over here is minus 4.34 minus, and then y2 is minus 5.19. And then we divide this by x1, which is 0.003095 minus x2, which is 0.00339. All right. So this is going to give us an answer to the gradient that we will use in the next part. So the gradient turns out to be minus 2,881.4, but it asks us for the gradient in 3 significant figures. So I have to write it up till here, and the 1 is going to be dropped off. We get a 0. So this is going to be minus 2880. That will be my gradient. Make sure you round correctly. I've already told you this before. All right, next. So now over here, we have the relationship between the log of initial rate, that was our y-axis values, equals constant minus EA, that's the activation energy, divided by 2.303 times R, this is the ideal gas constant, times T, right? Now, if I rewrite this last bit over here, I'm going to get minus EA over 2.303 R times 1 over T. So this 1 over T over here is the quantity on the x-axis, and whatever multiplies with this x-axis quantity, this expression over here will be equal to the gradient. All right. So now, if I need to find the activation energy, I'm going to equate this entire expression to the gradient. So this is minus 2880 equals the minus activation energy divided by 2.303 times R. Now R is 8.31. All right. So once I perform this calculation, the activation energy, the value turns out to be minus 55,117. All right. Now, because we've been using the gradient to 3 significant figures, so I need to round this up to 3 significant figures as well. It's only fair. So this is going to be minus 55,100. All right. Now here's the thing. The units of activation energy are kilojoules per mole, and this answer seems way too large for kilojoules per mole. So just to make absolutely sure, what I will do over here is I will compare units, okay? So we know that the gradient has a unit of Kelvin, right? So I need this entire expression to have a unit of Kelvin as well. Okay, so the ideal gas constant, we know that it has a unit of joule per Kelvin per mole, right? Now this Kelvin could come upstairs and it'll become just Kelvin, all right? And in order to make sure that only Kelvin is up there, nothing else, the activation energy needs to be in joules per mole. And so these cancel out, and all you're left with is the Kelvin. So this activation energy, by the way, is in joules per mole. So you need to convert this, divide by 1,000, and you're going to get the answer of 55.1 kilojoules per mole. By the way, this negative sign shouldn't even be there. This is positive, right? These negative signs on both sides should cancel out. Activation energy is never negative. Silly me. Anyway, it says it is not possible to repeat the investigation. State whether the data from the investigation is reliable, right? Now, we cannot repeat an average. That's not an option. So we need to just judge based on what we have, whether the data is reliable. Now the problem is that if you look at the graph once again, the graph generally looks fine except for this anomalous point. Because we have one anomalous point, we do not know if we were to continue this experiment, how many more would show up. So it's not reliable, unfortunately. So that's what we're going to say. I'm going to say no, because there is an anomalous point. All right, so that concludes paper 5, variant 2 of May-June 2022. So hopefully you have understood how to do a lot of things like drawing diagrams, doing calculations, rounding, drawing the graph, calculating gradient, identifying anomalous point, all that stuff that comes up a lot in paper 5. So if you have any questions, drop them in the comments, and if you like this video, do subscribe to the channel, and I'll see you in the next video.